Hi, welcome to the Organic Chemistry Lab series in my Organic Chemistry channel. In this video, I will talk about aspirin synthesis. What is aspirin? Aspirin is a well-known drug. It is used as an analgesic, a pain reliever, antibiotic, a fever reducer, and an anti-inflammatory drug. The active ingredient in aspirin is acetyl salicylic acid. At the beginning, salicylic acid was used and it had the same therapeutic effects as acetyl salicylic acid. However, because of the presence of this phenol group, salicylic acid was irritating to the stomach. So the manufacturing company did an esterification reaction and it added this acetyl group to form acetyl salicylic acid, which is known to have a less irritating effect to the stomach. So currently aspirin contains acetyl salicylic acid as the active ingredient. It has a molar mass of 180 grams per mole. The melting point of acetyl salicylic acid is between 133 to 135 degrees. It is a water-insoluble compound, however, it's soluble in ethanol. If we look closely at the structure of aspirin, we can see that we have two functional groups. The main one of them is the carboxylic acid functional group, and the second one is the ester functional group. Aspirin or acetyl salicylic acid is prepared by esterification of salicylic acid. In this reaction, the hydroxyl group of the salicylic acid reacts with the carboxylic acid or a carboxylic acid derivative. So usually to make aspirin, we start with the salicylic acid. The OH group, so salicylic acid here is acting as an alcohol in the esterification reaction through this OH group. And then we are going to add a carboxylic acid or a carboxylic acid derivative, as we will see in a second, in order to add this ester group. Now it's known that to make esters, we can make them either from carboxylic acids or carboxylic acid derivatives which are above them in the reactivity series. And based on this, we can prepare acetyl salicylic acid either by reacting salicylic acid with acetic acid or acetyl chloride or acetic anhydride. Now, usually reactions with acyl chlorides are very fast. However, they have the problem of producing the toxic compound, which is HCl, and the reaction is so vigorous and it cannot be controlled. That's why preparing acetyl salicylic acid in this way is not a good idea. The second method that can be used to make acetyl salicylic acid is by using acetic acid. The reaction in this case is slow. It is usually catalyzed by acids. However, the byproduct, which is water, hydrolyzes aspirin. So it leads to the hydrolysis of aspirin, which means that it brings it back to the salicylic acid form, and that's why this reaction is usually low yield and it's not highly favorable to be used in the lab. The best option is to use an acid anhydride, which is acetic anhydride, because in this case the reaction is faster than using acids but slower than using acetyl chloride, so it's somehow controllable. And also the byproduct is acetic acid, which doesn't cause any problem in regarding the yield. So in this experiment, we will be using salicylic acid and acetic hydride to make acetyl salicylic acid or aspirin. Synthesis of aspirin using acetic anhydride. This is an acid catalyzed esterification reaction, so we will be using H2SO4 as a catalyst. The reaction is exothermic. It produces heat, and the reaction is complete, so it's not an irreversible reaction. Experimentally, we are going to mix salicylic acid, which is a white powder, with acetic anhydride under the hood, because it has toxic fumes, and then we will add a few drops of H2SO4. We are going to stir with a glass rod the reaction mixture. The temperature will start to increase, so you can feel the flask being hotter, and this indicates that the reaction starts. And then we will continue stirring for about 10 minutes until the reaction starts to drop, and this indicates that the reaction is complete. Usually after this time, a white solid, which is aspirin, will start to appear. If it didn't appear, then we can either cool it down or add some water, as we will see later on. So we will add cold water, and then place the whole beaker which contains the reaction mixture in an ice bath, and this is to precipitate aspirin and increase its yield. Because I mentioned in the first slide that aspirin is not soluble in water. That's why adding cold water will help aspirin to precipitate, and this will increase our yield. We have to be careful because adding cold water is used to hydrolyze acetic anhydride. So we have there are two main reasons for using cold water. The first one is to precipitate aspirin, and the second one is to hydrolyze acetic anhydride, which is used in excess. If we used hot water will cause hydrolysis of aspirin. So as I said before, hydrolysis is breaking of the ester group and forming the salicylic acid back. Finally, we are going to collect the crystals by vacuum filtration, and then we will check their purity with a melting point test. Usually the melting point of pure aspirin is between 133 to 135 degrees. So the purity of aspirin can be checked in two ways, either by using the melting point test. If you remember before, we talked about the melting point and the importance of the melting point. Usually if you measure the melting point of a solid and you notice that there is a wide range, or if you notice that the melting point is lower than the literature value, this indicates that the solid is not pure. So this is one way of determining whether our aspirin is pure or not. We are going to check the melting point. If the melting point range was very narrow and it's very close to the 133, 135 range, this indicates that our aspirin is pure. If not, then this indicates that it's an impure sample and we have to purify it using recrystallization, because usually crystallization is the best way to purify solids. The second way that can be used to to check for the purity of acetyl salicylic acid is the ferric chloride test. The ferric chloride test is usually used to detect the presence of phenols. So usually the ferric chloride test is used to detect if we have the phenol group. Now, in this reaction, one of the byproducts or one of the things that can contaminate aspirin is the presence of salicylic acid, so unreacted salicylic acid. Now, salicylic acid has this OH group, this phenol group. So if you want to check whether our sample contains salicylic acid or not, we can use the iron chloride test, which has a yellowish color. And if we notice that the yellowish color turned into a purple color, this indicates that our sample is actually contaminated with salicylic acid and it has to be purified. Finally, let's talk briefly about the calculations. Now, depending on the mass of salicylic acid that you started with, you divide it by the molecular weight, which is 138. And in this way, you can get the number of moles of salicylic acid. Usually this is used in excess, so it's not going to be the limiting reagent, and that's why our calculations will be based on salicylic acid, and this is how we are going to determine the number of moles or the mass of acetyl salicylic acid. So basically, using the mass of salicylic acid, we will determine the number of moles of salicylic acid, and then the number of moles of salicylic acid will be equal to the number of moles of acetyl salicylic acid or aspirin. And based on that, we can calculate the theoretical mass of aspirin, which is equal to the number of moles of aspirin times 180.16 grams per mole. And then to determine the percentage yield of the reaction, you just have to divide the actual mass, which is the mass that you obtained in the lab experimentally, by the theoretical mass of aspirin, and then you multiply this by 100, and this is how you calculate the percentage yield of your reaction. Of course, we have to make sure that our aspirin is dry. It doesn't contain a solvent, otherwise the mass could be very high, and this is due to the presence of a solvent. Thank you.